Hi everyone, I'm Polezero. In this video, we're going to dive into BLDC motor speed control. We'll explore the fundamental principles of PWM, various driving methods, and then move step by step into PI speed control. Before we get started, don't forget to hit the like button and subscribe. First, let's look at PWM, or pulse width modulation. This is a technique that controls the ratio between the on and off times of a pulse. In this example, you can see how PWM adjusts the brightness of an LED by regulating its average voltage. By increasing the duty cycle, which is the percentage of on time, the average voltage rises and the LED gets brighter. This is the core of PWM control. The final average voltage is simply the input voltage multiplied by a duty cycle ranging from 0 to 100%. The waveform you see now shows a BLDC motor running in 6-step mode without PWM, relying strictly on Hall sensor signals. To control the motor's speed effectively, we must regulate the average voltage entering the motor, and that's where PWM comes in. There are two main approaches. First, bipolar control, where both the high side and low side switches of the inverter are controlled via PWM. On the other hand, we have unipolar control, which applies PWM to only one switch, either high side or low side. Currently on the screen, only the high side switch duty is being adjusted to regulate the average voltage. And in this next waveform, you can see the speed being controlled by modulating only the low side switch. Let's take a moment to discuss switching loss in an inverter. MOSFETs and IGBTs are primarily used as switching elements, but in the real world, these devices experience a split-second delay when turning on and off. As you can see on the screen, the overlap of voltage and current during these transitions creates energy loss, which is released as heat. Now, let's compare unipolar and bipolar control. In unipolar mode, only one switch is modulated, resulting in lower switching loss. Bipolar control, however, switches two paths at a high frequency, leading to nearly double the switching loss compared to the unipolar method. This is why high-power systems often adopt unipolar control to minimize heat generation and improve efficiency. Next, let's look at how we measure motor speed using Hall sensors. First is the M method. As the motor rotates and generates Hall sensor pulses, the M method counts the number of rising or falling edges within a fixed measurement time. We then calculate the RPM using the formula shown here. This method is quite accurate at high speeds where pulses are frequent. However, at low speeds, the limited number of pulses leads to lower resolution and a higher margin of error. To compensate for this, we use the T method. Instead of counting pulses, we measure the time interval between one edge and the next using a high-speed timer clock in the microcontroller. The RPM is then calculated based on this duration. The T method is highly precise at low speeds because many more clock cycles fit between the edges. Conversely, at high speeds, the clock count decreases, which increases the error. To summarize, the M method is better for high speeds, while the T method excels at low speeds. For those looking for the best of both worlds, the MT method is also widely used, so I recommend looking that up if you're interested. Now let's take a deep dive into the PI speed control system for BLDC motors. A typical speed control loop is structured as you see here. When we input the desired command speed, the system calculates the difference from the current speed measured by the Hall sensors. This difference, or the error, becomes the input for the PI controller. The controller then calculates the appropriate PWM duty to bring that error to zero, adjusting the voltage applied to the motor accordingly. Let's look closer at what's happening inside the controller. First, with proportional control, or P control, increasing the gain helps reach the target speed faster. However, This can lead to overshoot, and it inherently leaves a steady-state error, meaning it never quite reaches the exact target. That's where integral control, or eye control, comes in. It accumulates the error over time to completely eliminate that steady-state offset. However, it responds more slowly, and if the gain is too high, the system may begin to vibrate or oscillate. A PI controller combines the best of both worlds, balancing the fast response of P control with the precision of I control. Let's examine the actual waveforms during PI speed control. Starting from a standstill, we've given a command for 1000 RPM. You'll see the error peak instantly, causing the controller output to surge. This applies maximum torque, allowing the motor to reach 1000 RPM very quickly. Now, let's apply a load. The moment the load hits, there's a brief undershoot where the speed drops. However, the PI controller immediately detects this and increases the torque to overcome the resistance, returning the motor steadily to 1000 RPM. This stability under varying loads is why PI control is so essential. However, Hall sensor-based 6-step control has one structural limitation: torque ripple during commutation. Looking at the waveforms, the left shows the 3-phase current, and the right shows the torque. Even with minimal load, you can see pulses in the torque every time a phase switches, or commutes, based on the Hall sensor signals. This pulsation is the primary drawback of 6-step driving, and it persists even when a constant load is applied. Over the last 2 videos, we've explored the driving principles and control methods of BLDC motors. In our next series, we'll discuss PMSM and vector control, which can dramatically reduce this torque ripple and offer even smoother performance. Thank you for watching, and I'll see you in the next video.